In this video here, we're going to take a look at the planarity algorithm. Now let's just start here then by discussing what it means for a graph to be planar. So a planar graph is one that can be drawn in a plane such that no two edges meet except at a vertex. And by using the planarity algorithm, we can determine whether a graph is planar. So what I've got here is two graphs. Now both of these graphs have edges crossing, so at first glance then, we would just assume that neither is planar. However, K4, that's this graph here, and you should be familiar with these graphs, by the way, when we went through special types of graphs, right? We introduced these types of graphs here, complete graphs, okay? So K4 can be drawn with no edges crossing. And if we were to do that, it would look, say, something like this. Now, the same cannot be done with K5, so it follows that K4 is planar, but K5 is not planar. And this version of K4 shows the same connections, but this time no edges cross. So let's just take a formal look now at the planarity algorithm. So the planarity algorithm can be applied to graphs that contain a Hamiltonian cycle by following these 6 steps. So for step 1 then, what we need to do here is identify a Hamiltonian cycle. Step 2, we then draw a polygon with vertices labeled to match the ones in the Hamiltonian cycle. And just to make life easier here, if you can, just draw a regular polygon. Now for step 3, we then draw edges inside the polygon to match the edges of the original graph, not already represented by the polygon itself. For step 4, we then make a list of all edges that are inside the polygon, and we could do this in any order. So the order that you do this, it really doesn't matter, completely up to you. Now for step 5, we then choose any unlabeled edge in your list and label it I. If all the edges are now labeled, then the graph is planar. And then finally, for the very last step here, step 6, what we now do is look at any unlabeled edges that cross the edge or edges just labeled. Now, if there are none, we just go back to step 5. If any of these edges cross each other, then the graph is non-planar. If none of these edges cross each other, give them the opposite label to the edge or edges just labeled. And then finally, if all edges are now labeled, the graph is planar. Otherwise, all we do here is just go back to the start of step 6. So in terms of the planarity algorithm here, I think kind of explaining it like this in 6 steps isn't particularly intuitive. I think the best way to really demonstrate this is just run through a quick practice question. So to finish with for this video here, let's just run through one practice question together. So let's just get started here then with this practice question. Now, as we can see then for this question here, we have this graph, right? And we also have part A and part B. So for the first part of this question here then, all we want to do here is just complete a Hamiltonian cycle for the graph above that starts A, E, B. So for part A then, as we just said then, all we want here is a Hamiltonian cycle. So Hamiltonian cycle. And this starts in A, E, B. Okay? So we go from A to E, E to B. So from B here, let's go to F. So we'll go from F to C. We'll then go from C to D. And then finally, just go back to A, right? So AEB, FC, FC, D, A. Okay? And this here then is our Hamiltonian cycle. And it is important that we get this correct here because obviously for the planarity algorithm, we do need a Hamiltonian cycle. Okay? And as you can see as well, the question is structured in such a way to help you answer this question. Okay? So there we have it then. That gives us the solution to part A, hopefully nice and straightforward. Now for the next part of this question, part B, it just says then using the planarity algorithm, show that the graph above is planar. Right, so where do we begin here? So once we've identified the Hamiltonian cycle here, what we now do then is draw this graph here as a polygon, okay? So I've got how many vertices here? So I've got 6 vertices, so I'm going to draw a hexagon here. It doesn't have to be perfect, but obviously just try to make it look somewhat neat. So if I draw it, say something like this. So these are my 6 vertices here. If I just join these up then, we'll get something like the following. Like I said, it doesn't have to be a masterpiece. As long as we can kind of follow along, that's absolutely fine. Now, do be careful in how you label the nodes here, or the vertices. So we have to follow the Hamiltonian cycle here. So if this vertex here is A, the next vertex here along must also be in this order, right? So this is A, this must be E. In that case, then this must be B here. This must be F. This must be C. And then finally, this here must be D, right? We just follow the order of our Hamiltonian cycle. Now, clearly, this graph here is not isomorphic to this graph here. So what we need to do then is add some edges inside the polygon here to ensure that this graph is isomorphic to this graph here. Okay? Now, obviously, just take your time with this and just kind of go back to this graph here. So what I can see then is vertex A here has order 3. At this point here, it's got order 2. So A connects to E and A connects to D. Now, on the original graph here, A connects to D, A connects to E, and A also connects to C. So I need to make the same connection here inside the polygon. So something like this is absolutely fine. Perfect. And once I've got the correct order here for my vertex, I'll give it a tick. Okay, just to ensure then that I know that this vertex here is correct. Moving on then, vertex E here. So vertex E here has order 4. At this point here, it's only got order 2. So E connects to B and E connects to A here. Clearly, the same is true here. So E connects to A and E connects to B, but E also connects to C. So E connects to C, like so. And E also connects to D, like so. Okay, it's now got order 4, so we give it a tick. Perfect. We just keep going around here. So for vertex B here, at this point we've got order 2. Vertex B here has order 3. So B connects to E, like we can see here. B also connects to F, as we can see here. What are we missing then? B connects to D? Yeah. So B connects to D, right? And we'll just join those up like so. Perfect. We'll give that a tick. Vertex F then has order 2 here. And clearly it's got order 2 here. So F connects to B and F connects to C. Perfect. We'll give that a tick. What about C then? So C here has order 4, right? And for our graph here, what have we got? 1, 2, 3, 4. Perfect. We'll give C a tick. And then for D here, what did we have? Order 4. 1, 2, 3, 4. Perfect. Good stuff. So this graph here is isomorphic to this graph here. And at this point now, we can start applying the planarity algorithm. Okay. So for the next step here, what I'm now going to do then is list the edges inside the polygon. Okay. So underneath then, edges in polygon. So edges in the polygon are given as, so what have we got here? So we've got AC. So AC. What else do we have here? We've got DE. So from D to E. We've also got from D to B. So D to B. And then finally, what am I missing here? C to E, right? Perfect. Okay. So we've got 4 edges inside the polygon. Now, to be fair, this is a pretty straightforward example of the planarity algorithm. After this video, I'm also going to do a second video here on the planarity algorithm with a slightly more complicated example. But for now, I think, a more straightforward example is quite good just to introduce the idea then of the planarity algorithm. Now, for the next step here, what I'm going to do here is just choose any edge inside the polygon. And I label that as I. Now, I like to just work from left to right here. So I start with AC as being inside the polygon. And I label that with an I here. Like so. Okay. What do we do next? So what I do here is I check any edges that cross the inside edge here. The one that we just labeled, right? AC. So I can see 2 edges here cross AC. I'll just go over these in a different color. So what I'll do then is I'll do this in orange. So this is AC here. That's the one that we're concerned about at the moment. So what edges intersect with AC? So I've got DE here, like so, and also DB, okay? They're the two edges here that intersect with AC, the edge that we labeled as inside the polygon. Now, what do we do here then? So what I'm looking to check here is whether these two edges that we've just kind of identified basically as intersecting with AC, do they intersect each other? Well, no, they don't. I know they meet at a single point here, but that's absolutely fine. If they intersected at any point here, then what that would tell us is the graph above would be non-planar, okay? But they don't intersect, so that's absolutely fine here. So DB and DE here cross AC. They don't intersect, as we've already mentioned. So what I do here then, if I just go back to my original pen color, is I mark DE and DB as O here. We're going to make those outside the polygon, okay? And we'll do that later on, but for now, we'll just label these as O and O, okay? Perfect. So up to now, all good. Now, what we're looking for here is for every edge inside the polygon to be labeled. Now, at this point here, we've labeled AC, we've labeled DE, we've also labeled DB, but we haven't labeled CE here, okay? So we need to just keep going here. So I go back to the two edges that we just identified here. And what I'm looking to check then is whether any edges cross these two edges that we've just identified. So I'll do this in a different color to the one that we've just used here. Let's just do it in green. So AC, we've already covered that. So that's fine. We don't need to worry about that. It's already labeled as well. So that's fine. However, CE here does cross. Okay. That intersects then with DB, sorry. Okay. So CE here intersects with DB. Now, it doesn't cross, obviously it's just a single edge, so it doesn't cross anything else. So again, it doesn't mean that the graph here is non-planar. That's absolutely fine. And because it intersects here with DB, then in that case, we use the opposite sign again. So we did I here for inside. Once we identified what intersected with AC, we change that. So we always go from I to O, and then again, we alternate here. So for CE then, this will stay inside the polygon, okay? So hopefully that made sense. So we just alternate here, put an I there, like so for CE. So AC is inside the polygon, DE and DB will be outside the polygon, and CE will also be inside the polygon, okay? We've now labeled every edge inside the polygon, so perfect. What that means here then is this graph, the one that we started with here, is planar. And what we can do then is draw this. So let's show my amazing art skills here. So again, I'm just going to draw the polygon. We'll do it over here, so we've got a little bit more room. So I've got my vertices here. Again, my art skills are never the best, but it doesn't matter too much. As long as we can kind of follow along here, that's absolutely fine. So again, make sure that these match up correctly. So A, E, B, F, C, and D here. Now we just join these up then. Get something like this. Clearly these should be straight lines. I appreciate my art skills are shocking. Oops, that is pretty bad. I'll do that one again. It's that bad. Try again. Second time is the charm here. There we go. And then finally here. Something like this. It's not perfect, but it doesn't matter too much. So AC here starts, sorry, not starts, but stays inside the polygon. So A to C here, like so. So AC stays inside the polygon. CE also stays inside the polygon, like so. Perfect. And then D to E goes outside the polygon. So D to E here goes outside the polygon. We'll get something like that. And also DB goes outside the polygon. So bit of a long edge here, or a long arc, but it doesn't matter too much. We'll get something like that, okay? And there we have it. What I'll do, I'll just go over the arcs that I've changed here. So, or we kind of modified here. So DE now goes outside the polygon, and the same is true here for DB as well, okay? These are the two that have gone outside the polygon here. And I'll just mark all the vertices in red, just so it's a little bit clearer here, what I've got then, okay? And there we have it. As you can see then, none of the edges here now are intersecting as the original graph demonstrated. Okay. And there we have it. So how amazing is that, right? For decision maths, I think that is pretty good. Don't tell me that isn't the best thing that you've ever seen for decision maths up to now. To be honest, it's probably the most interesting thing, in my opinion, for decision maths. The planarity algorithm. It's pretty cool. Like you can see, demonstrating whether a graph is planar. Okay. Anyway, there we go. That is the solution for this one practice question. And that brings us to the end then of this video here on the planarity algorithm. Oh, actually, before I end the video, I did forget to mention that the graph is actually planar. So let's just do that as well. So therefore, the graph is planar. The graph is planar. The graph is planar as all edges are labeled. Okay. Labeled. There we go. See, that's how exciting the planarity algorithm is. I forgot to actually finish the question. So there we go. That gives us the solution to the one practice question. And now we can actually finish the video. So that brings us to the end then of this video here on the planarity algorithm.